Welcome back everyone. In this lecture, as I promised, we will actually see the construction of Verma module, and then we will actually define the irreducible module as quotients of this Verma module. So, let us recall what we have done so far. Okay. So, you start with lambda being dominant weight. So, we have constructed these irreducible modules corresponding to this lambda dominant. So, this is the irreducible, of course, finite dimensional representation, but this is also highest weight representation and corresponding to lambda. So, this is the most important thing. But if you think about it, this V lambda is indeed generated by this highest weight vector V lambda. So, highest weight vector, and this highest weight vector is actually unique up to scalar, that also we have seen. So, now using PBW basis, we also observe that this is indeed generated by UN minus acting on this V lambda. So, what is the observation? The main observation is this is just a highest weight vector. So, we need to have these following relations. H V lambda must be equal to lambda of H V lambda, and that is true for all H in H. So, that is the first observation. The second observation, when you apply x on V lambda, that should be 0 for all x in n plus. So, these two are most important relations that we have for V lambda. So, can we actually use this to somewhat construct universally some highest weight representation? So, basically you just demand your representation has these two properties. Okay. So, basically it is a cyclic representation generated by some vector, highest weight vector V. So, that is what we want to actually construct. So, how do we go about it? The best way to actually go about it, instead of looking at G representations, we will actually pass to the universal enveloping algebra representations. So, those representations are actually easy to understand, at least easy to construct, okay, because UG being associative algebra. So, note that this is associative C algebra. So, if you are interested in constructing representations of UG, especially cyclic representations, then they corresponds to basically two sided ideal in just left ideals inside UG. So, let us say we are only considering the left ideals. Okay. So, cyclic UG representations corresponds to left ideals. Okay. So, what I mean by that? So, basically what you want to do, you want to actually construct some representation that has this property. Okay. It is generated by V lambda and then has these relations. So, then what you can do, you can simply take this I lambda to be the left ideal, generated by H minus lambda of H1. So, where 1 corresponds to the generator of C inside your UG. Okay. So, 1 is the like 0th component of the UG. So, because C naturally sits inside UG, so that is your span of that is the 1. So, now you take H minus lambda of H in H, and then you take all n plus. If you take the left ideal generated by these two, then naturally what you can do, you can just go modulo this, and that you can define to be our z of lambda. Then you can easily see that this 1 plus I lambda, which we call it V lambda. So, this is going to generate your z lambda. Okay, so z lambda is given by UG V lambda. So that's obvious. Now note that H lambda of H must be 0 inside your z of lambda. So that simply translates when you take H, apply it on V lambda. So then you get exactly lambda of H V lambda. Similarly, X V lambda is going to kill inside Z lambda. So X V lambda must be 0, and this is true for all H in H and X in N plus. So you are simply demanding the relations that you needed, that is all, and then you are just going modulo that, then you get the I module, G module or UG module, so which is cyclic module that has these relations. Okay. So now it is easy to see that V lambda is indeed highest weight vector, and this is highest weight representation in the usual sense. So now once we have this, then immediately we can conclude the following. So I will write it as a theorem, which is indeed observation which we have made already, but in this setting also the similar observation is true. Now since we have the PBW basis, now using the PBW basis you can easily see that Z of lambda is indeed equal to UN minus applied on V lambda. So because all n plus elements kills, the H part acts as scalar, so only the n minus parts will give you something important. So this is the first statement. The second statement, if you take the Z of lambda, then this is given by the span of all this PBW type basis comes from this UN minus acting on this V lambda. So it's basically y beta 1 power R1 etc. y beta n power Rn applied on V lambda as before in the highest weight representation. So in particularly we can actually take these vectors and then see. So these vectors y beta 1 R1 etc. y beta n Rn applied on V lambda, they lie inside the weight space of Z lambda, which has exactly mu. The weight is given by lambda minus R1 beta 1 plus etc. plus Rn beta n. So if this is non-zero, then that corresponds to the weight lambda minus R1 beta 1 plus etc. Rn beta n. Okay. Since these are all actually spanning, so we can find a basis of this spanning set and then form a basis of Z lambda, which consisting of weight vectors. So that tells you that Z lambda is indeed H weight module. So we have the weight decomposition. So Z lambda can be written as direct sum of Z lambda mu, where mu runs over the weights of Z lambda. So this observation 3 says if the weight is survives, then that must be less than or equal to lambda, because the mu must be of the form lambda minus R1 beta 1 plus etc. Rn beta n. So now once you fix the tuples R1 etc. Rn, then you can easily see that because this beta 1 etc. beta n, they are nothing but some ordering on the positive roots, and alpha 1 etc. alpha small n, that will actually form a basis of the H, okay, H star. So that tells you that given this R1 etc. Rn or given mu, okay, there could be only finitely many tuples. Okay. So let me make it very precise. Z lambda mu. So this is going to be spanned over C such that you take y beta 1 power R1 etc. y beta n power Rn applied on V lambda. Now these tuples chosen such a way that, so this should have a constraint, okay. So, this will be spanned, but these R1 etc. Rn must satisfy mu equal to lambda minus R1 beta 1 plus etc. plus Rn beta n. Okay. So, that means if you fix mu, then we are already fixing lambda. So, then this lambda minus mu becomes this R1 beta 1 plus etc. plus Rn beta n. Okay. If you rewrite this in terms of the alpha I basis, then you can easily see that, because this Ris will becomes combination of coefficients that comes from alpha I basis, and there will be only finitely many choices, because given R1 there will be only finitely many, given. Okay, so let us write lambda minus mu as some summation k I alpha I range from 1 to n. Now, these ki's are fixed. Because these ki's are fixed, so you can easily see that there will be only finitely many tuples R1 etc. Rn, such that this vector will be equal to this given vector. Okay. So, this proves that z lambda mu has only finite dimension, okay, for all nu less than or equal to lambda. So, it could be 0, we do not know. Okay. So, now if we actually look at the highest weight space and look at this dimension. So, the dimension of the highest weight space must be 1. Indeed, that highest weight space is spanned by V lambda. Okay. And as sixth corollary, we can see that Z lambda is indeed indecomposable G model. Indecomposable G model. So, why this is true? So, let us say it is decomposable, then it will can be written as some V direct sum W. Then look at this lambda weight space, then it will be sum of the corresponding weight spaces. So, that you would imply that either V lambda is 0 or W lambda is 0. Okay. So, let us without loss of generality assume that W lambda is 0, then V lambda must be equal to Z lambda lambda. So, since the lambda weight space in Z lambda is one dimensional. So, that tells this V lambda is inside V. Okay, this proves that this, and that says that V must be equal to Z of lambda. There is no other option. So, that proves Z of lambda is indecomposable. Now, if we actually use this all this information, then we can actually conclude that you have a unique maximal submodule of Z of lambda. Let us call it max of lambda. So, this is the sum of all proper submodules of Z lambda, and this is the unique maximal submodule. Okay. Obviously, the sum of all proper submodules will be submodule, that is not a problem. The only thing that we need to prove is it must be proper. If it is not proper, then it could be equal to like entire Z of lambda. In that case, we are not having any maximal submodule. Okay. So, we have to prove that this is indeed proper. Okay. So, the way you can actually see this, if you consider this max lambda weight space. So, the dimension of this, it can be either 0 or 1, because this has to be a subspace of Z lambda of lambda, which is one dimensional. Okay. And if it is one dimensional, this max lambda, then that would force that this max lambda is being equal to your actually entire module Z of lambda. But the thing is, we are taking the sum of all proper submodules of Z lambda. Okay. So, if you take any proper submodule, then if you look at the lambda weight space, that must be 0. So, that will force that in this sum side the lambda weight space must be 0, there is nothing there. So, that forces that this cannot happen, this a max of lambda cannot be having dimension 1. So, that means at least the lambda weight space is 0. So, it avoids that maximal weight vector. So, that forces that the max of lambda is indeed proper inside your Z of lambda. So, now this actually kind of immediately says, because it is the unique maximal submodule, then there is this unique irreducible quotient. So, that we denote it by V of lambda. So, there will not be any confusion, okay, because this V of lambda later we will prove that for lambda dominant it will be finite dimensional module. So, which will be isomorphic to the V of lambda that we already constructed, because once we prove it is irreducible, then it is highest weight representation, finite dimensional. So, it must be isomorphic to the V of lambda that we constructed. Okay. So, now let us actually look at this Z of lambda. Okay. So, it is actually easy to see that there is no other highest weight vector. Okay. If you have another highest weight vector inside Z of lambda, let us call it W. So, W being another highest weight vector. So, that means it can have highest weight some mu. So, then it is immediate that mu must be less than or equal to lambda and lambda must be less than or equal to mu, then that will force that lambda equal to mu. Okay. So, now because lambda is mu, W must lie inside this one dimensional space C V lambda, that will force that W is some non-zero scalar multiple of V lambda. Okay. So, that means up to scalar multiple there is a unique maximal like highest weight vector or maximal vector. So, the theorem that we are interested in proving, let me state it here. So, for we have let us say lambda in H star. So, then we have this irreducible module defined by this lambda, which is called V of lambda. So, we want to understand when it is finite dimensional. So, we can prove that it is finite dimensional if and only if lambda being dominant. Okay. Note that if lambda is dominant, we already constructed another irreducible module corresponding to lambda. Since there is unique highest weight representation of weight lambda, so there is no confusion. This module will be naturally isomorphic to that module that we already constructed. So, now let us prove actually at least the one way. Okay. So, here is the step 1. So, V of lambda is finite dimensional implies lambda being dominant. So, this is exactly same as the proof that we have for V is highest weight representation and it is let us say you take V to be highest weight representation, then the highest weight being dominant. Okay. Similar proof works here. So, recall what we did. So, look at this SL2 copy span by xi, hi, yi, okay, which is isomorphic to SL2. Then look at USI module generated by this V lambda. Then one can prove that this is indeed isomorphic to the irreducible module corresponds to V of lambda of H. Okay, I will leave this as exercise, because if you look at this module, one can prove that this will be span of y v lambda, yi v lambda up to etcetera yi lambda of hi v lambda. Okay. So, yi lambda of hi plus 1 v lambda will become 0. So, this is indeed irreducible SL2 module, irreducible SL2 module isomorphic to V of lambda of hi. Since this lambda of hi being the highest weight for this irreducible module, lambda of hi must be non-negative integer. That comes from the representation theory of SL2. So, that proves that lambda must be dominant. Okay. And now, using the similar argument, one can see that if you take any weight of V lambda, that also must be integral weight. So, if mu is a weight, then mu of hi must be integer. Again, you can use the SL2 representation theory. So, we can actually prove something more, because this is being so this is important to note that V of lambda is also a highest weight representation, and it is a highest weight representation that corresponds to lambda. Okay. So, this is something immediate, because being quotient of z of lambda, we always have, if you take V lambda bar to be the image of V lambda inside V of lambda, then it h must act as lambda, and all n plus will kill, that is obvious. Okay. So, that is why it is highest weight representation, but it need not be finite dimensional. So, that is something that we do not know, but if it is finite dimensional, then we know that it is the representation that we constructed earlier. So, that is why this lambda must be dominant, and we also have the following observations. If you take the weight of V lambda, then this Sn plus 1 acts on this. Okay. Not only that, the dimension of V lambda mu will be same as dimension of V lambda W mu for all W in Sn plus 1 and mu in V weight of lambda. So, weight of V of lambda. So, this is something we already proved for lambda being dominant. Okay. So, that is why it is continuing to be true here. Okay. Otherwise, the same proof that we have seen using SL2 theory works here. Okay. You can actually run through the same proof. So, now if you are interested in proving the converse, okay, so that is actually that if lambda dominant, then that implies V lambda is finite dimensional. Okay, to prove the converse, let us observe something. To prove the converse, look at this z lambda modulo the max of lambda, that is what we are interested in. We are calling it as V lambda. Okay. So, if lambda is dominant, there is no reason that this quotient is finite dimensional. Okay. But we are expecting it to be finite dimensional, then it becomes finite dimensional irreducible module. In particular, it is finite dimensional highest weight representation. So, whatever observation that we made before must be true here. In particularly, Sn plus 1 must act on the weight of V lambda. So, that is the first thing to prove. And the second thing to prove, if you look at the dimension of this V lambda mu, so that should be equal to the dimension of V lambda W mu for all mu in weight of V lambda and W in Sn plus 1. So, for this representation also, okay, we must have this, otherwise we can't expect it to be irreducible, sorry, finite dimensional representation. So, this is actually the first step towards proving that this V lambda is indeed finite dimensional. So, let me just write the idea. So, we will work it out later. So, first we will prove that there is this natural action of Sn plus 1 on the weights of V lambda. To get that, it is enough to actually get action of the generator, which is Si. Okay. To get the action of the generator, what we will do, we have to use the SL2 representation rate. So, the step 1 will be, so first construct non-trivial finite dimensional Si submodule inside this V lambda. So, basically we want to construct something that is similar to this submodule generated by V lambda. Okay. So, that is the first step. The second step, we want to say that V lambda, it could be infinite dimensional, but it is direct sum of finite dimensional SL2 modules. Okay, it is a direct sum of, so it is enough to say just a sum of finite dimensional Si submodules. If we say this, then it is immediate that because the element Si acts on the finite dimensional finite dimensional SL2 modules. Okay. So, obviously it will act on the sum as well, okay, and it will preserve the dimension. So, bringing down here matters a lot. Then after that we will use the information that SL2 acts naturally on the finite dimensional representation of SL2. Okay. So, and of course, so what corresponds to Si we have to see. Okay, we will construct very explicit automorphism of this V lambda. Okay, that automorphism will corresponds to this Si. So, that actually will tell you immediately that, because automorphism is going to preserve dimensions. So, if you take the muth weight space, then it will send it to the automorphism Si mu weight space. So, because it is an automorphism, so it is going to preserve the dimension. So, that is the way we prove that dimension of V lambda mu is same as dimension of V lambda W mu. Okay. So, all these things actually requires lots of work. So, we will actually go step by step and then try to prove all these things. Then later, so we will actually use this very important information that given to us, that is lambda being actually dominant. If lambda is dominant, okay, and then if you look at all these elements mu in lambda such that which is smaller than actually, so let us call it mu is in lambda plus, so that lambda is bigger than mu. So, one can prove that this set is finite. Okay. And since, so the weights, so ultimately we will prove the weights of V lambda can be obtained by Sn plus 1 action on this set mu in lambda plus lambda greater than or equal to mu. So, this set being finite will imply that whatever the way Sn plus 1 acts, because Sn plus 1 is finite group. So, that is not going to give you like more elements. So, it is going to be finite. So, that way you say that the weights of V lambda is finite. Already you know that the weight spaces actually are finite dimensional. So, that will prove that. So, once you have the all the weights are finite. So, since weight spaces are finite, that would force that V lambda is finite dimensional. So, many things are involved in this proof. Okay, we can go step by step and then we will ultimately prove this. Okay, I will stop here and then we will continue in the next class with the proof of this. Thank you.